All right. So I just quickly remind you what we have done last week. And we will come back to this. Remember, this set PS of A is just an arbitrary set with some points, and you look at probability on it. So it means you look at numbers on these points such that these numbers are sum to 1. So it means you're going to take a linear combination of these three things with some ratio given by this number. So this is the set of finite probability distribution, or with finite support. And we say that two such functions, so there are functions on this set, one is bigger than the other one, if there exists a U such that you have such an inequality. So what you do, you sum this over all points in this set, the function at this point, and this new function U at this point. And we will see this today. So we say that we have an order on these two elements of PSA if you have such an inequality. And please be aware that this is just an inequality between numbers. Okay. With U a function which associates to any point in A, a real number. Okay, we will come back to this, it will play a role. Now I introduce also what is an n-player strategic game. It's two things, it's a set A and a payoff or utility functions. What is A? A is just the product of all strategies for each player. So AI is a strategy, the set of possible strategy for one player, the player I. And like for R2, where you do R times R, you do this, I explained it last time, you do this product of all strategy for the n players, and it's called the set of strategy profiles. This is one element here is a strategy profile. And we define also U as just the collection of all individual payoff functions. So this payoff, each of them is a function from A to R. So if you have n of them, you need an here and Rn here. Okay. Then in such a strategic game, we assume that all players play simultaneously and independently and rationally, which means they want to increase their payoff. The game is to get the best payoff. And I gave an example of the prisoner dilemma and also this Kono oligopoly. And I gave the third one. Now I also introduce, so you have this big set A of all possible strategies. And there are specific points which are called Nash equilibrium. It's a point in this big set such that for each payoff function, the value at this specific point is bigger than, you take the same variable except the I1, so except the I1, and the value at this point has to be bigger than all the other ones. So you took all possible values for this variable, and at this point it has to be bigger or equal. And the idea is if you move away from this point, by definition, you cannot gain anything if you're the only one moving away from this point. And then what is quite a famous theorem is this Nash theorem, which gives you sufficient condition for the existence of such a point. In fact, we will use it today and it will become more clear. Last week it was a bit abstract, but we will see that today it's exactly what we need. And then I introduced some specific strategic game. It's first for two players only, but also with a zero sum. What does it mean, zero sum? It means what one, I mean, it's exactly this equality. U1 of A1, A2 is minus U2 of A1, A2. So it means what the payoff of player one is negative the payoff of player two, or if you put on the same side of the equality, it makes zero. That's why it's called a zero-sum game. And because U2 is completely defined by U1, to describe such a zero-sum game, you just need these two sets, A1 and A2, and one payoff function. You don't need the two because the other one is obtained by just putting a minus sign. And then when you're in this setting, I introduced two functions. I didn't write the definition, but you can find the definition. There is this lambda underline and this lambda with overline. So the first one is the worst payoff for player 1, while the second one is the maximum loss for player 2. If you look at the definition, it's quite clear. And then from the first one, you can define the minimum payoff that player 1 can guarantee. So if he plays correctly, he's sure to get this payoff. So it's by a specific choice of what he has to do, or a specific choice of his strategy. And the same from the second function, you get the maximum loss that player 2 can suffer. It means he can lose more, but if he plays correctly, at most he will lose this. So this is his payoff. And because of this relation, it means this maximum loss for the player 2 is also equal to the maximum payoff for the player 1, because it's exactly the opposite. And we finally prove that this value is small or equal to this one. This was the last argument. So I know it's a lot of information. I encourage you to read at least once, or better 2 times or 3 times the notes. And I also put a kind of summary, which is exactly what is here on the blackboard. If you can understand the summary, it means that you have a good idea of what was going on. You can ask me at any question at any time. I just continue on this. We have seen an inequality, but it may happen that we have an equality. So if these two numbers are equal, and if they are equal, we call these two numbers, or the value you obtain, we call it V, and we say that this game G is strictly determined. And in fact, this is the easiest situation, because look at these two sentences. One is a maximum payoff for 1. The other one is a minimum payoff for 1. So it means when these two numbers are equal, if both players play correctly, the first player will exactly get this value. So it's determined. That's why it's called strictly determined in this case. And we say also that G has a value. And this value is precisely V, this number. So it's the easiest situation, and in fact, it appears quite often for this zero-sum game. See. Now you can wonder, if there is such an equality, do you have a strategy to get to this? So do you have a point which gives you exactly this value? So you have a way to get these values? The answer is no, not always. Why? I just remind you something from calculus 1. Take the function x goes to x on the interval 0, 1. What is the maximum value or the supremum value of this function on this interval? Do you reach 1? No. So it means, of course, it's just an analog. It means even though you can compute that the supremum value or the maximum in this case is 1, it doesn't mean you reach it. You can be as close as possible to it. So you can be very close, but you will never be exactly at 1. So the same can happen here. Look at the definition of this function. It's an infimum or a supremum. It doesn't mean you exactly reach it with 1 point. It means you can be as close as possible to this point. So it's a small subtlety. So if there exists a strategy A1 in this such that this underlying function is exactly equal to this value. So if you reach this value by a certain strategy, this strategy is called an optimal strategy. But it doesn't, even if we are in this setting with an equality, it doesn't always exist. So if there exists A1, we say that A1 is an optimal strategy. It's an optimal strategy for player one. I just write one, but you have to understand it means for player one. And similarly, if I use also this sign, which means they exist. If they exist, A2 in A2 such that it's exactly the same sentence, but now it's for lambda over line A2 is this, exactly this value, then A2 is an optimal strategy for player two. But again, even if we are in this best situation, this is, you can think about it as the best situation, and we see that, in fact, we very often obtain them. We are very often in this situation. It doesn't mean that you have an optimal strategy. You may have a strategy which leads you to a very close value, but not exactly this one. Okay. Now, if these two values are not equal, the outcome is less clear. So you cannot a priori say what is going to happen. I mean, there is more you cannot distribute the difference between these two values can be either for one or for the other one. So you don't know what is going to happen. But we will see, as I said, we are very often in this situation. Okay, this is what we said for zero-sum game. But before studying zero-sum game, I introduced Nash equilibrium, which I recalled. So you can wonder what is the relation between these optimal strategies, if they exist, and Nash equilibrium. What is the relation? Nash equilibrium was introduced before, so it means it was more general. So what is the relation? What is the relation with Nash equilibrium? And in fact, I just remind you what means Nash equilibrium. It means for the first player, it's a point which satisfies this U1 of A1 star is bigger or equal to U1 at A1, A2 star for any A1. And the second condition means U2 of A star, A2 star is bigger or equal to U2 of A1 star, A2. But there is no A2 because we are in a zero-sum game. So it means this is minus U1 of A star 1, A2 star, bigger or equal to minus U1 of A1 star, A2, because they are just a minus. So if you look at this inequality and this one, what do we obtain? If you have already attended Calculus 2, it should remind you something. So look, we have U1 of A star 1, A2 star is bigger or equal to U1 of A1, A2 star for any A1. And the other one, if I multiply by minus, we get that this is smaller or equal to U1 of A1 star, A2 for any A2, right? What does it remind you? Sorry? No. No, I don't take a limit. It's what is called a mountain pass point. So look, in one direction, this A1 is a maximum. So you have a maximum at A1 star. But in the other direction, in the perpendicular direction, if you do a picture, you have the opposite. A2 star is always smaller or equal to A2. So just think about a mountain pass. You have in one direction, it's a minimum. In the other direction, it's a maximum. This is exactly what we have. So it implies that a Nash equilibrium is a mountain pass point. It's also called a saddle point. This is another name for this. If you don't have a picture in mind, just Google this or look at Wikipedia, you can find pictures for U1. So Nash equilibrium is such a point. And now I wanted to do the relation between optimal strategy and Nash equilibrium. Let me state a result. If somebody is interested in doing the proof, it's not so difficult. So it's a theorem. So let G is equal to A1, A2, U1. It means it's a two-player zero-sum game. If I take a point A1 star, A2 star, which is a Nash equilibrium, So it means a mountain pass point of the function U1. Then you can compute U1 at A star, A1 star, A2 star. And in fact, it's equal to V. And so it means, which means G is strictly determined. G is strictly, so we are in the best situation, it's strictly determined. And in fact, we have more than this on these 2 point AI star is an optimal strategy for player I. So it means a Nash equilibrium. If you have a Nash equilibrium, it means the two value lambda overline and lambda underline are equal. So you are in a strictly determined game, and the value of V is given by this value, and you have even the two optimal strategies. And the converse is also true. So what means the converse? Try to guess the converse is also true. So what does it mean? It means if you have a point, first, if the game is strictly determined and you have two optimal strategies, then this point, A1 star, A2 star, is a Nash equilibrium. So it goes in the two directions. So you have an equivalence between Nash equilibrium and the existence of a Nash equilibrium. By the way, it might not be unique. You may have more than one. It depends on U1, on the payoff function. But if you have one, it means that the game is strictly determined, and it gives you the two optimal strategies. And the proof, I gave the reference. But once again, keep in mind, Nash equilibrium was defined before studying zero-sum game. So it means it was a more general concept. It turns out that for zero-sum games, we introduce the notion of optimal strategies on this V. These two concepts coincide, but Nash equilibrium is more general. Okay. Do you have any question here or online? If you have any question online, you can also interrupt me. Okay. So what we have seen so far is called a pure strategy. So you have this set AI, and you can choose either this strategy, this one, or this one. We built everything on this. Now I would like to take a kind of linear combination of this. I don't want to take only this strategy, but I want to take half of this strategy and half of this one. Okay. So this is what we are going to do now. So this is now that this, what I represented by these things, where I take functions with which sum at one is going to play a role. The interpretation is I will not only play this or this, I will take half of this strategy and half of this strategy. So we need to introduce this formalism. So it's a bit complicated. So please try to think about it. And if you think about it for a few minutes, you will understand. It's not so complicated, but it's not trivial. It took me one day to understand it. Mixed strategies. But you're better because you're younger. Mixed strategy for finite games. What do I mean by finite? I mean this picture is not correct. I have only a finite number of points. So I will give the precise definition, but it means you have only a finite number of pure strategy. So what is I can write it here. The definition of a finite game, let G be this A and U be a strategy game. We say that G is finite if each AJ or AI is finite. So it means if each player has only a finite number of strategies before taking linear combination. So this is the definition. A finite game means each player or each agent has only a finite number of options. And okay, this is a definition. I just observe that if AI contains, I need to give a number, contains a certain number MI elements, it can be different for each player. That's why I put a different number. So if AI contains MI elements, then how many elements are in A? Can you tell me how many elements in A? Do it for 2 first. Sorry? Yes, it's M1 times M2 times M3 up to Mn, which I can write simply the product I from 1 up to n of Mi. Think about in 2 dimensions, you remember the product means you have 4 options for one player. Let's say you have 3 options for the second player, and then you have to take all these points. Okay, sorry. I did it like this. If one player has 4, the other has 3, then altogether you have 12. Okay. And of course, if all of them has m elements, so now if all these numbers are the same, then A contains m power n elements. This is just m times m times m times m. But this is annoying. Why is it annoying? Remember in the last section, I put a lot of emphasis on linear combinations and on convex sets. Can you have a convex set containing only 12 points? No. Remember, a convex set, whenever you have 2 points, you should be able to take any linear combinations. So you have an infinite number. Remember, linear, it means lambda times x plus 1 minus, I use t, 1 minus ty. If y and x are in the set, all these points have to be in the set. So if you have only a finite number of points, this is not possible. So any convex set has to contain an infinite number of points. So it means AI and A cannot be convex set, which is a bit annoying because last week I emphasized some result for convex set. So we need to correct this. And how are we going to do it? We are precisely going to deal with this picture. So I recall it once again, that this TS of AI is the set of probability and I will explain it again in a second. Observe that last time when I introduced this set, I said that they have to have finite support. But now I'm dealing with finite set. So you don't need an additional condition because at most you have mi points. So it's finite. So the set of probability function on AI, and I just mentioned the condition that the support, we had this condition, the support of P is an element in this set. The support of P is automatically finite if AI is finite. And today we deal with finite sets. So I don't need to add this condition. I will change the notation because you will see there is a much better notation. So let me do the picture again. Suppose we have AI which contains 3 points. Suppose we have these 3 points. Okay. I take the simplest case. AI has only 3 elements. I want to consider all functions which sum up to 1. So I assume that the sum 1/4, 1/2, 1/4, it makes 1. Or if I take a different one, I have 1/3, 1/3, 1/3. Okay. So the set of all these functions is this one. Okay. But there is an easier way to do it. Observe that this PS of AI with AI containing, let's say, M elements. I just take M. Or keep the same notation, Mi elements. I can represent it like this, is equal to, I will take the set of vectors, x1, x2, up to xmi. You know what is a vector in Rmi. Think about 3 dimensions, so you take a point in 3 dimensions. I only want positive values. This function take only positive values. So I don't take -1, which means I only consider 0 infinity. This is R plus. And what is the condition? The condition is this vector, or these different contributions, have to sum up to 1. So it's a set of x1 up to xmi in this mi dimensional space, such that the sum x1, xi, I from 1 up, no, xj. I should not use the same, I is fixed. The sum x, the first one plus the second one plus the third one and so on, is equal to 1. Do you agree that you are describing all such functions? Above all points, you take a number, the blue one, for example, they have to sum up to 1. So I put these 3 numbers in such a vector with the condition that this sum is 1. It's the same. And this guy has a name. Maybe some of you have seen. And the notation is SMI. It's called a simplex. So you can, I put a link to the Wikipedia page. A simplex, it's used in many different fields. But it's just a vector such that it's in R plus. So it's each component is positive or 0, but it sums up to 1. And it's called a simplex. So let's just have an example. If we have only one element in the set, how do you describe the first one, S1? No, it's S0. If you have, no, it's S1. S1 is just, indeed, it's just the value 1, because you have only a function on one point which has to sum up to 1. That's it. S2, you can represent it like this. You have first direction, second direction, and this is a set of all points which sum up to 1. S3, now you need to go in 3 dimensions, and you observe quite quickly that it's a triangle like this, which goes through these 3 values like this. So you have a triangle which is on a corner. And I let you guess what is S4. I cannot represent it easily because I would have to go in 4 dimensions. But in fact, S4 is like a tetrahedron. Okay.
Of the same straight line or a triangle.
So,
we only have discrete numbers of.
No. Here it takes arbitrary values.
How the axis is straight line?
We are in R3. Okay. The second one, we are in R2. I have points in R2 or R2 plus, which sum up to 1. So no, it's really the entire line. It's S2 is really this, and S3 is really a triangle. with the entire triangle, not just its boundary. No. These are called simplices, or simplex, or simplices. So it means instead of considering this abstract space of functions, I can just deal with vectors. Vectors which sum up, or the components sum up to 1, which is much simpler. So please think about it. This is not too complicated. It's just a different description of the same set. If you have this image in mind, you can easily see, oh, if you take all such functions, you can draw exactly what is here. Any question or remark? And what is the aim? What is the idea? I told you, these 3 points are what we consider up to now. These are pure strategies. So either one player chooses this one, or this one. Now I want to be able to take 1/3 of this strategy, 1/3 of this one, 1/3 of this one. Or 1/4, 1/2, 1/4. So now we have more freedom. So now we want to give, this is called mixed strategies, because it's a mixture, mixed strategies to all players, So instead of just having a finite set of strategies, they can now, each of them can now make a combination like this of the different strategies. Okay, so now I give you the main definition. Okay, so we start with a game. It's G is this game up to now with the n player strategy game. And I will assume that it's finite. So in the sense I introduced, so n players finite, in the sense that each set AI is finite. Now, this is called the mixed extension. Oh, by the way, I will spend quite a long time today on one example. So don't worry if you don't understand at the beginning this definition. When I will really do the details on one example, and we will see exactly everything. So the mixed extension of this game, of G, it's a new game, is a new strategy game. N player, it contains the same number of players, is a new N players strategy game. And it's denoted by E of G. E is for extension. And if it is a strategy game, it has to be defined by 2 objects. So the first object, I will call it P. And the second one, in the notes, I use a specific font for U. On the blackboard, it's difficult to do 2 different views. So I use a color. But if you look in the font, in the notes, it's a different hue. So it's going to be a set P and so this is going to be the set of all strategy profiles, and U is going to be a payoff function, but I have to describe it now, or I describe them. Okay, maybe I go here simply because I want to keep this picture for a second. So what is P? So with, you can maybe guess what is P. I want to give this freedom to all players to do linear combination. So it means I want to for P1, for the player who has these 3 pure strategies, I want to give this set of possible strategies. So P is going to be P1 up to Pn. It's a set of n points with Pi, with Pi belonging to Ps of AI, which I also denote by, I will now use this notation, SMI. I told you I identify this set with simply a subset of this vector space. So each player can, the first player can take any of these functions. Then another player, let's say the second player who has 4 possible pure strategies, can take any function summing up to 1 on these 4 points. So each player can now take any mixed strategy. So this is all mixed strategies, or any mixed PI is any mixed strategy for player 1, for player I. So this is the set P. It's a set of all mixed strategies for all players. Okay. And I want to say how P acts on A, because these are functions on the set A. So let me give you one formula. So I should write on P. This, oh, I didn't write, sorry, I should call this. So this is capital P, but I should say the set of P of this form. P is P1 up to Pn. So it's like a vector. And P is a function from A to R plus, no, to, yes, R plus defined by. So I need to give you this information. P of A, it's P of A1, A2 up to AN. And it's quite simple. It's a P1 of A1 times P2 of A2 Pn of A. Okay, this is probably a bit abstract. I mean, I give a definition. It means A is a set of, it contains the strategy of the first player, strategy of the second player, and so on. I apply a P. P itself is a vector. And you just take the first entry applied to the first one, second entry applied to the second one, up to the Pn entry applied to the nth entry. And if you think about it, this is P is one of these functions. Let's say the blue one. So it means this is a number between 0 and 1. This is a number between 0 and 1. This is a number between 0 and 1. So you are just multiplying numbers between 0 and 1. So it means this is a number between 0 and 1. So when you evaluate P at one point of A, P is this vector, you just get a number between 0. Again, I will work on an example very soon. And so I define what is P. Now this P is made of mixed strategies for each player, because we want to give this freedom. And what is a red U? Or in the notes, it's a Gothic U, but in the blackboard, it's a red U. So I need to give a definition. This red U is, so this is 2. This red U is equal to, it has also n components. And it's the same as before. Before, the U had also n components. Before it was from AN to Rn. Now A is replaced by Pn to Rn. And it's defined by, yes, defined by U entry I on a A, no, sorry, on a P. On a P. Okay, it's a definition, but we will see that it's the meaningful one. Some A over A of P of A times UI. Okay, I told you, please concentrate on. And there is a difference between the red one and the white one. I started with one game. Remember, the game was GU. U was a function or is made of U1 up to UN. And each of them, UI, is a function from the set of all strategies to R. Now, what I'm saying that I define this red UI. It's a set on mixed strategies. And I simply have to take into account all mixed strategies multiplied by UI, this one, at A. Again, we will work on an example. So I define what is a mixed extension. So from one game, I define a new one, which looks complicated, but we will see that this is really natural.
How we can define this because the A is not convex, it is also final. So how we can define UI?
A was, this set A was, this one?
Yes.
It was in the definition I started with the game.
I did the utility function.
Yes.
So like A is a finite, it's not a convex.
No, A is not convex, but let me now write the exercise that you are going to solve. Thank you. So now you can. Wait a second. You will see exercise for you or anybody else. No, everything is well defined. Check that precisely this. Okay, there are 3 points. That for any P in this capital P, the first is that when you sum the P of A, you get 1, A in A. This is just to check that this new function P is also a probability function, and it's on a finite set, so this is well defined. So it implies that, in particular, this small p is in PS of A. Okay, this is the first point. Second point, check that this P now, this set of all mixed strategies is convex. This is what is convex. Because you can, we don't have the picture anymore, but because we can take such linear combinations of mixed strategies, it's a convex set. It's convex. And 3, check that this red U is a linear utility function. I encourage you, it's not difficult. This exercise is not difficult. What is difficult is to understand the definitions. But I encourage you to think about this exercise, because as I said, the exercise itself is rather simple. You just have to write a few equalities. Wait a second. But in order to do this exercise, you need to think about the definitions. Yes. No. Okay, I have two different, sorry. It is this P. This P. Okay, I should use the same font. Otherwise, you check the note. It is this capital P. Now, this P is convex, so this is a convex set. So it means A was not convex, but the set I have introduced here of all mixed strategies is a convex set. So in order to fully understand the definition, I encourage you to look at this exercise. And you can wonder, oh, why do we call it a mixed extension? Mixed, we understand. Mixed is because we have mixtures. But why extension? Extension is usually when you have something and you put it in something bigger. This is typically an extension. So why? In fact, I'm claiming that A is inside this P. But you need to identify A with elements of P. So just let me write briefly this. Why extension? I already mentioned a bit of this last week. So for any A, which is an element A1, A2, up to AN inside A, I set a certain function, PAI, from AI to R plus. What is this function? I'm going to choose, remember, I have my set here, and I consider functions like this, sum up to 1. But I can also consider the function which takes the value 1 at one point and 0 elsewhere. It's one function. So I consider the function which I indicate by 1 point with, it takes the value, this special function AI takes the value 1 exactly at this point, and it takes the value 0 everywhere else for any beta I in AI and beta I different from AI. So it means I just define, it's like a Kronecker delta. For those who know, I define the function which takes the value 1 exactly at AI and 0 everywhere else. It's an element of this PS of AI. So it means I associate to any point in AI a function. And now I define PA simply as this function PA1, PA2 up to PAN. And observe that this function, what is the value of this function? Again, it's like a Kronecker delta. This function PA at A, it's a product of this function evaluated at A1, this function evaluated at the second point, this blah, blah, blah. So it takes exactly the value 1, and PA at any B is 0 for any B inside A, B different from A. So it means A is included in P simply by taking the function which takes the value 1 at this point and at 0 elsewhere. So this is an inclusion of A in the set of functions. Just by a point, I associate the function which is 1 at this point and 0 elsewhere. And the second observation, now you can wonder what is the value of the red U entry I at this specific point. So you use the formula. I gave a formula for this. It's a sum over all B. I have to use B because A is already used. So at every point in A of this specific function at B times UI at B. Now, can you tell me what is this value? It's UI at A. Because look, it's almost always 0, except when B is A. So it makes ui at A, which means not only I manage to have A inside P as a specific function which takes the value 1 at this point and elsewhere 0, but in addition, the new payoff function on this specific function is precisely equal to what I had before. In this sense, it's an extension. I've put A inside P in a specific way, but in addition, I respect the value of the payoff I at A. Now it's the same payoff I at this specific point. So it is an extension. Okay. See, no, the theory is well developed. And what is the main theorem now in this framework? So if we try to summarize, we started with a game which is finite, and I put it in a bigger context where I accept mixed strategies. So every player can play a mixture of everything. So the very good point is that in this framework, so in what I have introduced, I don't recall the framework. We start with a finite game. We do the mixed extension. E of G has a Nash equilibrium. So it means, and in fact, this is, just for information, it's an application of Nash theorem. You remember I mentioned Nash theorem last week, probably, and I said, oh, we cannot apply it to the examples I mentioned because they were not in a convex setting and so on. But now we are in it. I mentioned we have convex set. These simplices, so these SM, which are also P, or SMI, which are Pn of PSAI, they are convex. They are bounded. If you look at the picture I made, either this or a triangle, they are bounded. They are closed. So you can really check the assumptions of Nash theorem. We are exactly in the framework of Nash theorem. So in fact, it's an exercise to prove this statement, which is not difficult. You just check that now you are in the setting of Nash theorem. Not more than this. Okay, so I told you I will spend some time on a very explicit example. You might be disappointed at the end, but still it's interesting to do everything on one example. So, example. I didn't present it, but it's in the notes. It's called the mixed extension of what is called the matching pennies. Matching pennies game. So it is a game where you have two players, each say an integer, and you look at these two integers, they can be even or odd. You do the sum. If the sum is even, one player win. If the sum is odd, it is the other. So one say I suppose that it will be even, the other one odd. You take these two numbers, you do the sum, you check, and one wins, one loss. So we are going to do the mixed extension of this. So two players, we have two players giving each an integer. And we look for the parity. Parity means even or odd. Of the sum. This is the framework. But this is before the mixed extension. So A before the mixed extension, it means we had only 2 points in the strategies, either you say even or odd, and which means A contains 4 values. It's like the 2 prisoner. You have these 4 points, which is a product of these 2 sets. So you have either EE, EO, OE, or OO, which means it's the two number that the 2 players say, either it's even, or even odd, or odd, even, or odd, odd. And you look at the sum, and let's say the player say it's going to be even, then if the first player say it's even, he's going to win in the first and in the last case. If the second player say odd, he will win in the second and in the third case. Okay, so what about mixed strategies? Mixed strategies. So now the first player is going to say, player 1, he's going to say that here, now we have these 2 points, E and O. He's going to say, oh, I assume that it will take the value E with probability a certain number. And of course, we have 1 minus this number for the other one because it's going to sum to 1. And A1 is any number between 0 and 1. So the first player say, I suppose that it's going to be E with probability A1, O with probability 1 minus A1. And of course, the second player has also some freedom. So he say, oh no, it's going to be E with probability A2 and O with probability 1 minus A2. And again, A2 is any number between 0. So we have defined the set of all functions on these 2 points for each player. Each player has 2 strategies. He can consider all these mixed strategies. So now I consider P. If you look, I have to consider these 2 functions. And we have to compute P of EE. Look, by the definition I given, it's P1 of E times P2 of E. So this is A1, A2. Now you have P of EO. Look at the definition, it's P1 of E, P2 of O. It makes A1, 1 minus A2. Then we have P of OE is 1 minus A1, E2. And P of EOO is 1 minus A1, 1 minus. I'll just follow the definition I gave. You define P, which is these 2 mixed strategies, arbitrary mixed strategies, and you evaluate on any point of A. Okay? So it is in the thing of the definition of a mixed extension. Then I need to compute the red guy, the utility. So I need to compute U1 of this P. Now again, you look at the formula. It's, let me write it and I will explain, minus 1 times A1, 2 minus 1. Look at the formula I gave for U1. It's a sum over all points of A of, I just recall UI, the red UI at P. By definition, it was a sum on A of P of A, UI of A. So this P of A, I gave the 4 values there. And this, I didn't mention it, but it's in the notes. As I said, the first player wins when it's even, so it takes the value 1, it means wins, when the two numbers are even or when the two numbers are odd, and he loses when the two numbers are, the sum is odd, so that's why he gets -1 when the sum of these two numbers is odd. This is in a table which is in the note. So you can, this is a general formula, you can compute this, and I will simplify a little bit. It makes 4a1, a2 minus 2a1 minus 2a2 plus 1. And then I encourage you to check with the second one. I know the answer. In fact, it's minus a1, a2 plus 2a1 plus 2a2 minus. But it's the same, except that it's quite clear. The other guy loses when it's even. So you have -1 in these two cases, and you have +1 in these two cases. OK, so you get the payoff for these mixed strategies. And what we observe, oh, look, it's a zero-sum game, which is not surprising because, in fact, the initial game was zero-sum. So it means it's a zero-sum game. So it means we have some tools, because I developed some tools for zero-sum games. Yes. No, in this case, it's a zero-sum game because the initial game was a zero-sum, so the mixed extension is also zero-sum. But it might not be the case. So I'm going to simplify, just observe that, OK, it's visible here. What you see is the only thing which matters is a1 and a2. Why? It's a simplification. I do a simplification. This PS of EO, it contains only 2 points, is fully defined, is entirely defined by just a number, by A1 in 0, 1. And maybe you observed it before. If the first player say he put A1 on this, automatically he has to play 1 minus A1 on this. So I only need one information. I just need this number A1. Because if I decide to put A1, probability A1 on E, automatically it's 1 minus A1 on O. And the same for the second player. I only need or A2 inside 0, 1, because if you know the probability on one point, you know on the other one. That's clear. So it means the game is given by, so the EJ is given by a number between 0 and 1. This is A1. For the first player, a number between 0 and 1 for the second player. This is A2. And it's a zero-sum game, so you only need E1. So once you have these ingredients, once you know A1, you have all mixed strategies. You have the mixed strategies of the first player. Once you know A2, you have the mixed strategies of the second player, and U1 is defined here. Okay, it's just a simplification. You cannot do. Okay, but now it's a zero-sum game. So since zero-sum, we have developed something. We have developed these two functions. The first one, and I gave a meaning to it, but let me recall the definition. It is the infimum over A2 belonging to, now I use this simplification. A2 is just a number between 0 and 1 of U1. And if I want to be precise, I should write P. But again, P tells you which mixed strategy is taken by A1 by the first player and which strategy is taken by the second one, and it's entirely defined by the two numbers A1 and A2. So I can write U1 of A1, A2. It's a small abuse of notation, but I think it's understandable because precisely I mentioned this. So it's the infimum over A2 belonging to 0, 1 of this function, of this number. If you just look at it like this, it's not completely trivial what it is, but if you reorganize as in this way, for A1 minus 2, A2 minus 2A1 plus 1. Now I'm claiming you can compute this infimum. Check. I take the infimum over A2. If the parenthesis is positive, then I have better take 0. Because if I want a minimal number, if the parenthesis is positive, I take A2 is equal to 0. On the other hand, if the parenthesis is negative, it helps me to get a lower number. So I've better taking A2 is equal to 1. So we have three alternatives. So if A2 is smaller than 1/2, if A2 is 1/2, and if A2 is bigger than 1/2. So let's check. In the first case, this parenthesis is smaller than 0, right? So it means, oh, if it is smaller than 0, I have better put the number 1 here so that I get something very negative. And what I get is, if this is 1, we have this guy plus this guy, it makes minus, oh, is it? It makes, sorry, no, 2A1 minus 1, because it makes 4A1 minus 2A1. So it makes 2, and we have minus 2 plus 1, it makes minus 1. Now, if A2 is 0, if A2 is 0, no, if A1, sorry, if A1 is 1/2, sorry, if A1 is 1/2, what do you get? You get 0, because this parenthesis is 0, and so it doesn't matter which A2 you choose, and this one is 0. And now if A2 is positive, it, oh, okay, so sorry, I mixed two lines in my notes. It's A1, A1, sorry. Sorry, so I repeat, if this is parenthesis is negative, you take A2 is equal to 1, and you do the sum, you get this. If A1 is 1/2, everything is 0. If A1 is bigger, then this is positive. Since you want an infimum, you're going to take 0, and you get minus 2A1 plus 1. All right? So it's not difficult. You should just do it by yourself. And you can do the same thing for the second function, because we have two such functions. So this is the lower one, the upper one. I let you do it by yourself. We also have three cases. It makes minus 2A2 plus 1 if A2 smaller than 1, it's 0. It's exactly the same ID, but I let you do it 2A2 minus 1 if A2 is positive, bigger than 1/2. Okay. We have this, we have computed these functions. What is the next step is to compute this one. And to compute this one, look at the definition. In this case, you have to take the supremum value on this set, which is 0. You check. In fact, these two values are 0. There is a mistake. 1/2, yes. Yes, thank you. The 0 is here. Yes, thank you. I told you were better than me. Okay, so what it means here, remember, it means the game is fully, strictly, this new extension is strictly determined. Okay, and we are looking for optimal strategies. The optimal strategies are, do we reach this 0? The answer is yes. Optimal strategies is A1 is 1/2 because you get 0 for A1 is 1/2, and A2 is 1/2. What is the conclusion? I told you are going to be disappointed. What is the conclusion? We did everything, and what we obtain that for each player, you have better suppose that you get half of the time even, half of the time odd, which is not so surprising. It's a completely random game. So the best choice you can do is 1/2, 1/2. But we prove it. Okay. Sorry, it's hard to have examples which are not trivial. But look, it took us 20 minutes to do all the program. So it means these are the optimal strategies. We got them. They exist. And for this random game, so this is the conclusion for this random game. The best strategy is clearly is probability 1/2 for E and 1/2 for O, which again is not so surprising. Okay, do you have any question? Yes. So you prefer better? Okay. Okay, thank you. Next time you come to the blackboard. Okay. Any question? I wanted to do this example in detail because, yeah, we did everything.
2 players.
Yes. No, it's much more complicated for the 3 players. Probably you can do it, but already 0-sum game. Okay, for 3 players, you have more flexibility. No, Nash equilibrium was defined for any n players game.
And it is for the cooperative, like for the non-cooperative games, you like the utilitarian follow the dominant theory. If they are not follow like the dominant theory, so then we can not find the equilibrium.
Or it's a different question if you can obtain it or not. Here we obtain it for these 2-player games. If it's an n player, we have a definition. I'm not claiming that you can always get it. Okay, I want to start with one chapter, or one section, sorry, bimatrix games and matrix games. I don't want to spend so much time on this. In many books, they spend a lot of time, but it's essentially linear algebra. And in fact, there is no, it's more than linear. But I'm going to claim that there is nothing new. So I could just keep this section, but it's just a reformulation of what we have done in terms of matrices or 2 matrices. So it's important because in many textbooks, you will, as I said, they will emphasize a lot on this. So it's good to know what they are doing, but you will see we have already done everything. So we consider it's for 2 players. Consider 2 players. two players finite game, finite strategic game. I will reformulate. So now I have to make it calligraphic strategic game. Okay. Now, if we have only two players, I'm going to call A1, the elements, I'm going to call them L, or instead of A1, I will just write capital L, and it's going to consist, all strategies are just named by 1, 2, 3, 4, 5, up to L. That's the name of these strategies. And A2, I'm going to write M, and it's going to be a set 1, 2, up to M. So the strategies now have just a name like this, okay? I'm introducing some notations. I need some matrices. So I will denote by calligraphic A and calligraphic B a matrix which is, I hope you know this notation. So it's a matrix with n row, m columns. Okay, and the elements of, I know first year you may have not seen so many times matrices. Yes. Okay, just for you, I put a comma. But now if you have a matrix 2.5 to 2.5, what do you do? The elements of A are denoted. In the note, I don't think I put a comma. If you want, I can add it. But we are doing abstract. So LM will never be 2, 2. Okay. Are denoted by AIJ and BIJ. So the entries of the matrix, I'm going to denote them by AJ or BIJ like this. Okay. This is a notation. And the last thing, I'm going to use the set P, PS of L. Remember, now A1 is L. I'm just going to use this SM, which I have introduced, this simplices. And PS of M is just SM. So there is nothing new. I'm just listing some notations. L. Yeah, right. Thank you. Because it contains L elements. And the last thing I need to observe, now let's compute. So the elements here, as I mentioned, these are vectors. And by the way, vectors. So I will use the letter X for the vector in SL, a vector Y for a vector in SM. Be careful, I will always consider that they are vertical vectors. So for me, a vector is a vertical one. Probably in economics, they usually do the opposite, right? They usually use horizontal one, correct? So I keep my notation because in all my courses, I put vectors vertically. Okay, yes? Yeah, be abstract. For a second, the first guy has a first strategy, himself has a first strategy, second strategy, and so on. And the other guy calls the first strategy, second strategy. They might be different, but each one is allowed to use the first one, second one. So please observe that I consider vertical vectors. It makes a small change because then X transpose is a horizontal vector. And the same, I'm going to use curly A transpose. Where did I put it? Or maybe I don't need the transpose of A. I don't. Okay. So now compute UI I, so be careful of my notations. Why I'm allowed myself to write this? Because a strategy, a mixed strategy, I should use a function, but on these pure strategies, but I use this notation. So a mixed strategy is a X, which is one vector of ML entries, and the sum of these entries are 1. So U1 of, before I wrote U1 of P, but now, so it was P1, P2, but P1 is an element X in this set, P2 is in this set. So it's just the same thing, but with a slightly different notation. Now, if you look at the definition, it was a sum over all elements of A1 times A2. So it means a sum over all I between 1 up to L, all J between 1 and M, because these strategies are denoted by 1 up to L and 1 up to M, of what? Xi, Xj, U of I. So it's not difficult. You can check. I'm using exactly the same definition, except that I have slightly changed the notation because I want to come to a linear algebra framework. U was U1. It was evaluated on the points of A1, A2, but the point of A1 is 1 up to L, the point of A2 is 1 up to M. So it's the same thing. And I can rewrite this as a sum over I and a sum over J. Yes, Y. Thank you. Xi U1 of X of I J, Y J. These are just numbers, so I can put them in any order. And what do you observe? This should remind you linear algebra. This is nothing but the vector X transpose a matrix, the vector Y. Apply, and I need to give you the definition of A. Apply a matrix to Y, you get a new vector. Multiply by the horizontal vector, it gives you a number. Please, if you are not familiar with this, ask anybody who is second year. You should know this. And what is A? You can guess. A is a matrix given by the UI. So A given by its entry Aij is nothing but U1 of Ij. I put on the, oh yes. In my notes, is it on the left or on the right? Maybe it's on the right. I don't know. Which one is better? Which one?
There are about 8 different notations for the time square. We tend to use capitalized T on the one.
You choose. Yeah, okay. I will check in my notes if I'm consistent. You need to put either on the left or on the right. You can put capital letter. Similarly, let me finish this with this U2 on the red one, the red U2. This is, you should complain when something is serious. U2 with a red column. U2 of XY, you do the same computation. You are going to check that this is X, T, T, B, Y, or B. Forgive division by Bij is U2 of Ij. Okay, what I wanted to say is we can rephrase what we have done by using matrices. because I express the first utility function on this of this mixed extension with a matrix applied to a vertical vector. It gives you a vertical vector times a horizontal vector. It's like a scalar product. It gives you a number. The same for U2, this payoff for the second payoff for the mixed strategies is given in terms of, of B applied to Y product with this horizontal vector. B is given by these two. So we have rephrased. I was interrupted by Muyan for too long, so I just finished my sentence. Then the definition, because I can finish with this a bimatrix game is the mixed extension. This is the last thing I'm writing. It's a mixed extension of the finite game, which was given by L, M, U1, U2. That was the original game. And what is a mixed extension defined by, defined by SL, SM. This is a set of mixed strategies for the first player, the set of mixed strategies for the second player. The utility function for the first one is entirely defined by a matrix. The utility function of the second one is entirely defined by this matrix. And these two matrices are inside the set of L times M matrices with real entries. Okay, that's it. So we have rephrased one strategic game with the mixed extension of a strategic game, which is finite, by something which is these two sets containing all mixed strategies and two matrices. And now we can rephrase a few things in this language. We will do it next time. But as I said, there is nothing really new. It's just because you can see this in the literature. OK, thank you. See you next week. If you find some mistakes in the notes, you can tell me. Don't forget to write reports whenever you have time. Don't wait for too long. Also, new PACE students.